So this week we're going to take and still use the disk method, but we're going to rotate around the y-axis. So we're going to take this line, which is y equals x. Notice it starts at the origin. We're going to bound it by the line y equals 5. So it's going to come in here. So I have this region, this kind of triangular region. And what we're going to have to do is we're going to have to cut this one perpendicular to the axis of rotation. So let's go ahead and rotate it. And notice again, this ended at y equals 5. This is my x-axis and my y. So when I rotate this, I get this three-dimensional shape. And so we always cut so that I'm always getting this disk. And so the thickness of this disk is dy. You can see that it cuts my y-axis, and this is my radius. So if I pull off that disk, it's ever so thin that this slanted line will be so thin that it will look and appear to be just a vertical line there. So this is my dy. My r from here out, it'd be right here in my disk. And so what we're going to do is we're going to add up a whole bunch of those disks, but we're going to have to find their volume. So I'm first going to find area, which is pi r squared. So my pi is a constant. I can see my radius, no matter where I cut, it's always from the line to the axes. So that line is y equals x. But because I'm integrating, its thickness is dy, I have to put that line not in terms of x, but in terms of y. So I have my pi out in front because it's a constant. My radius is now y, and I'm going to square it. And my limits of integration are the little circles start at 0, my radius is 0, all the way up to this top part, which is 5, the y coordinate, because I'm cutting in y, so I'm cutting along this axis. So let's try another one that's not a line here. This is the parabola moved up 1, so that's why this is up here at 1. And if I bound it by the line y equals 4, this has a point, let's see, if y is equal to 4, x is the square root of 4 is 2, 2 plus 1 is 3, so that would be that point. And again, I'm going to rotate it around the y-axis, so this curve is going to rotate over here. Let me draw that just a little bit better. Okay, so again, it is a dy cut because I'm cutting that y-axis. And so if I do that, let's just kind of see what the shape here looks like. It's kind of got this lip on it. I'm going to do a cut. So again, I like to draw my cut here and label my radius. And it goes from this curve, which is y equals the square root of x plus 1. Notice the plus 1 is not inside the square root. So again, I'm going to find the volume, and I'm going to add up all these slices. And the slices begin down here. And they begin when, let's see, x is 0. So if I put a 0 in there, y is equal to 1. So my y's go from 1 to the very top, which is 4, the cutoff. So this up here is 4. This begins at 1. So I'm using my y coordinates because, again, I'm in dy. So volume is pi r squared. So now I need to find r. I see that r is from the axis of rotation, which is the y-axis, out to the outer edge. So what I need to do here is find this equation right here, not in terms of x, but in terms of y. So that means I'm going to solve for x. So I'm going to bring that 1 over, so that's a negative. And I'm going to square both sides. So as I square this, I get x. So this is going to be y minus 1. So it's pi. And then I need to take the r, which is that y minus 1. And then what I need to do is I need to square it. So it's pi r squared. And so if this is r, okay, and then what do I need to do to that? I believe I need to square that so that I now have r squared. Remember, this was r. This x value is the same as r. It's this distance from the curve over. So I'm not worried about the integration of this. I'm more worried about just the setup of it.